Yeah, thank you, Ilona, for the introduction. I came to Kaiserslautern after I finished my PhD in mathematics in 2005 and then started working at Fraunhofer Research Institute. And actually, my first industrial project partner was Ballard Power System. And so I started working on fuel cell research. And yeah, that unfortunately at this time, anything I show you in the next 20 minutes wasn't there. So we couldn't do all the nice things that I can show you now. And we had but the topic of the project was doing permeability computations and gas diffusion layers. So, but yeah, nothing of what I will show you in the next 20 minutes was available at that time. But we started working on it. And now 20 years later, it can all be done easily in GeoDict, and that's quite nice. So I will show you how to compute relative permeability in a compressed porous transport layer. And yeah, why do we need to compute this value? Just very quickly, probably all know this. We're looking here at an electrolyzer, and the porous transport layer is a gas diffusion layer or microporous layer, and this has to provide gas and water permeability. It's the same like in a fuel cell. And it has to operate under different saturation levels. So there's oxygen present as a bubble sometimes or not. In a fuel cell, there's the water in a bubble. So it's just the other way around. But it's the same question. And the layer is deformed through the clamping pressure that we have. Yeah? So it's not, if you look at it ex situ on a CT image, it's not the same as if you have built into the electrolyzer or fuel cell. So you have to look at different compression levels. So I will give a presentation here, how to do the structure generation with fiber geo, grain geo, how to apply compression on it, how to do then the single phase flow computation, and last but not least, how to do also the relative permeability. This is two-phase flow computations with GeoDict. And of course, not all computations will be so quick that they fit into the 20 minutes. So I will sometimes load some pre-computed results. So how does such a titanium porous transport layer look like? So if you Google it, that's one of the first hits. It points you to Becker's homepage, and they show you this kind of model here that you see there. And yeah, it consists of some fibers, and that looks like something that we can also do with GeoDict. And if you surf a little bit around on their page, you also get this picture. It looks also like a model. You get also some information of what typical porosities are and thicknesses for such titanium porous transport layers. And also in the internet, you can find micro-CT images done at Paul Scherrer Institute. They also of this exactly the same fiber type. Yeah, they have fiber diameters between 14 and 50 microns here. So yeah, let's take these values and try to do something in GeoDict that looks fairly familiar, and then do some simulations on it just to demonstrate how it works. So in GeoDict, to make a fiber structure, we have to use fiber geo, create fibers. Yeah, we open that, we choose first some domain size that fits here. I'll do something like 500, 500, 200. So this will be 1 millimeter in the XY and 400 in the thickness. We have to set a solid volume percentage. So the porosity, we take here the 77, so the upper end of what was there on the homepage. And well, we have to say what type of fibers we want to model. We remove the defaults and say, okay, we'll take some curved fibers with some circular cross-section. We have to set a diameter. We take also maybe here the 22 microns. That was the intermediate one there on the on this information. We have to make the fibers longer than the domain size so that they go through the whole domain. And well, one thing we have to set also is if we say we take curved fibers, we have to give some values for the curl. That's a little bit complicated to understand a little bit. We can here decide if the fibers tend to keep the local curvature or the local direction. So if you say they should take a little bit of both, so they don't do a zigzag, but they have to be a little bit smooth curves. And global straightness means if there's some global preferred direction to the orientation, the global orientation of the fiber, or if it's free to, if it bends, it can go in another direction. So that's one of the points where we say if we want to have some anisotropy that we usually have, we have to give it a little bit of a global direction. And if we want to have also it be in plane, we reduce randomness in the Z direction. So you can play around with these values a little bit. This is a little bit something that can be optimized to match a certain realistic structure, but we just take it for now. If we do it for modeling, we should remove the fiber overlap, but it takes some time to do that. So just for the demonstration, I let the fibers overlap with each other. Otherwise, I choose the without overlap, and then the fibers will not overlap in the resulting model. So if I do that and click on generate, just let it generate, and then we'll have the structure here in 2D. I switch to 3D. I have here the structure, and I will improve a little bit here on the visualization so that it shows a little bit nicer. So we have here now a structure, and we can see that fibers are still allowed to overlap here. But yeah, as I said, if I set the checkbox differently, then this overlap will be removed, and the fibers will not overlap, which is more realistic, but it takes a few minutes more to compute. So as these fibers are not only, well, the titanium fibers are actually sintered titanium fibers, and there's one way to model that I actually will shortly show, because I think it's unknown to many that these things exist. There is, in the grain geo, we have here sinter and crystallization, and you can actually use that not to model the sintering process, but to mimic kind of the effect of a sintering process. So it will just shrink the structure, so it keeps kind of the volume, the grammage, but not the volume. Yeah, so that's the effect, and I can set this to a shrinkage, and if I say it should shrink by 10%, it will actually compute for about 40 seconds, and it will, yeah, as I said, it will keep the grammage but reduce the volume, and it will do that by, actually it will keep the same voxel size, but the same amount of voxels, but reduce the voxel length and make all the fibers a little bit thicker and glue together, and then it mimics a little bit the effect of a sintering process. Yeah, you can check this out if it matches to your models. So yeah, you see here, it looks a lot denser here. Now, if I do this with sintering. So if I want to compress this structure later on, because I'm interested in the permeability under compression, because in situ it's compressed, I have to do a compression modeling with ElastoDict. So in ElastoDict offers a number of possibilities, and we have to choose the deformations. And in the deformations, I have to set, oh, this is still solid. This should be, the material should be titanium, of course. Yeah, so I have titanium. Yeah, well, it doesn't matter because it's only the this that has some stiffness. And I have to define the load case here. So the experiment, if I want to do compression, is I have to choose compression. Path control is okay. In the boundary conditions to the sides, I have to say it's confined. It's not free. The structure continues. So there's not I cannot just press it and there's free space in all the sides. I have a compression in Z direction, so that's the through plane, and then here I can define the load graph. I can say, okay, the stress goes from 0 to 10, the strain from 0 to 10%, or I can say, okay, if I want to compress it by 30%, I can decide, okay, I do 30% in 10 steps, and then I have this from 0 to 30 in steps of 3%. And I can do this simulation. So boundary conditions, I shouldn't choose periodic if the structure isn't periodic, because then I get some artifacts. So it's better to have symmetric or mixed, at least. Mixed means that at least in the compression direction, I have it symmetric. And now important also is that in the geometry handling, I select the calculate on deformed geometry. What does this mean? Well, if I do a 3% compression step, then fibers will touch with each other that haven't touched each other before the compression. So I get new contact points. So, and this will increase the stiffness of the material, but only if I take this into account in the next step, that the geometry has actually been deformed and I get new contacts. So if I make this one here, this means that I'll take this into account, because otherwise I just will have a linear stress strain curve, because it's a linear model. And if I'm not calculating on the deformed geometry, I will always calculate the compression step from the original geometry, and I just get a linear output. But if I take this, after this 3% compression, the structure will be resampled. I get new contacts and a stiffer structure as a result of that, and I will get this typical stress strain curve. It will be nonlinear. So that's important here in ElastoDict. And this one, I'm sorry, I can't let it run here. This takes a little bit too long. So I go to the pre-computed results and show what it looks like. So first of all, this was done on a different realization of the structure before so this is the structure before the compression. And afterwards, well, I have here the results. You get stress strain results. I can show the plot here. You have here the strain up to 30% in these 3% steps, and you can see that you have this nonlinear increase because you have additional stiffness due to new contacts. So here, under the visualization, you can actually select for all of the steps the deformed geometry, and you can just load it. Yeah? So you have the geometry available. If you load it, it shows the compressed geometry at this level. And now I can compute things just on this structure. I have it for everything, so I can just compute in FlowDict the flow. And this goes rather quickly. If I just compute the permeability in the Z direction in FlowDict, I can select, okay, it's water maybe in the transport layer. I don't have to change anything here because, yeah, for permeability, the exact pressure drop doesn't matter because I just have the proper, yeah, I just compute this permeability, and this will be the same. And I can leave all the default parameters and just click run and let this run for a while. And while it runs, I show a few slides. I can show the results here in this visualization. In this movie, we can see how the compression compresses this layer, and we see the deformed structure, and on the right-hand side also the von Mises stress on the right half of the structure. So what we can also do is, because the material is not uniformly compressed, because we have this channel rip pattern where it's compressed in between, we can also have a look at this and make a model like this, where we can put some of the rips or whatever pattern we have, and compress it. And then it looks like this. And I think we have seen this image a few times today, and that's because we are actually pretty proud that this now works. It's not so easy as it looks. It was several years of development, and if you would have asked me 20 years ago if such a simulation is possible, I think everybody would have agreed that it's not possible to do that. And yeah, I think sometimes in between, 10 years ago, I think Hyundai asked if can we do that. We said not this year, but next year, and that was a little bit too optimistic. It took a while longer, but now it really works nicely, I think, and just out of the box, and that's great in that case. Yeah, and you can analyze this compressed structure if you, for example, look at it with MATIC, the 2D density map. You can have a density histogram from the side, and you can see that there's a denser compression under the ribs. And yeah, you could also, if you choose different values, you can choose how big the rasterize it here. Yeah, so you can get some more other statistics there as well. So, but now we have these two things. When should you use what? So, I mean, the left-hand side here, this homogeneous material, this is the one that you should use if you want to determine a function of the material, like the permeability independence on compression rate and saturation rate, because then you need some homogeneous material model where you can compute permeability and you can compute saturation and compute the function. Yeah, so if you want to have a function for upscaling, you always use this one. You just have then under the channel and under the rib, you have a different local compression, and then you have it in a different position of this function. Yeah? But you still need to compute it from this model. This one you have to use if you're interested in kind of local effects. Yeah? If you want to know what is the compression under the channel at a certain pressure or under the ribs, and what is maybe a flow pathway from here to there under this in this special thing, then you have to look at the complete model with the channel and the ribs and analyze that. Yeah, and now if I switch back and everything works as we hoped for, we're exactly at 100%. Great. And the simulation is finished. And we get the permeability now. What did we do? We computed the permeability for this one compressed structure, and it's written in here. It's for the through plane. We don't have computed the one in the in-plane direction. Of course, if we just make the check marks, we get these values too. So now this is just a single permeability for single compression and fully saturated. Yeah. So if we want to have the results for the unsaturated or the relative permeabilities, we can do that in GeoDict. In GeoDict, we have relative permeability option, and we can, in the relative permeability, we have to choose how the water gas phases should be distributed. So we have here a drainage simulation, and if we're interested in the water phase permeability, so we have air bubbles intruding, so the displaced phase is in this case the water, and we can set here at which saturation levels we're interested. So maybe we know already that we don't have too much air in the flow, so we don't need to go from 0 to 1. We can maybe set a certain range that we're interested in. Yeah, I'm not choosing something here. And then here, okay, we have to choose what's invading fluid, what's displaced fluid. So we assume everything's initially filled with water. We have some invading fluid, some air, and yeah, that's set up here. And we have to compute in which direction we're interested in the permeability. So that is through plane again, but of course it could be also interesting to have the in-plane permeability, which would be X and Y. Because also in plane, some permeability is needed because it has to flow somewhere from the under the ribs to the channels, and that goes in plane. So it's not only a through plane flow that happens. Yeah, we set this up, and then yeah, we can compute it, but this also takes too long because it has to do this for all the spots. And also we have to do that for all the compression steps. So we get one result for every of the 10 steps. I can just open them. Link. And so we have here 10 different results. Just select them all. Okay, we don't see much, but I can combine them. That's rather nice. If I combine them into one plot, we get, and then enlarge this, we get some plots here for the I have computed for in-plane and through-plane direction. So for example, for the through-plane direction, we have now here 10 curves. So the red one here is the step 0, is the uncompressed. We have air saturation from 0 to 40%. And then if we go up with the compression level, we move down here. So that's then the function for the 30% compression, and here then up to 40% air saturation. So you could also plot that maybe in 3D. Yeah, so with on the x-axis you have the saturation, on the y-axis the compression, and then on the third dimension the permeability. So you get some kind of this shape, and in this function you could plug into some upscaled model, and you have the behavior of this material under compression and for different saturations. Yeah, and with that I just get back to the talk. And of course, if you have to do this, I use a macro. Yeah, I don't click through all the 10 steps and everything. I just make a macro where I make a for loop from 0 to 10. And in step 0, I take the uncompressed structure, and then I go through these 9 compression levels that I get, and then just always run the same computation on it. Yeah. And then I just collect the results. So that's how you do it. You don't click through all the, because yeah, this way you're also sure that you don't have any differences in the 10 runs, yeah, because it always runs through the same code. So in summary, I've shown you how to generate a 3D structure model of sintered titanium fiber felt. How, yeah, you can of course vary diameter, porosity, curvature. I just made one quick example of a structure that looks some way realistic. Yeah, it's not some specific structure. I've shown you how you could use GeoDict to mimic sintering. I've shown how you can model in-situ compression. You can do that homogeneously or with this flow channel pattern, and then how you can determine transport properties as a function of the local density and local saturation. And of course, you cannot just do that for permeability. You can also do that for diffusivity or conductivity. Now, except that conductivity maybe is not so much from saturation. And yeah, with that, I thank you for your attention.